the loudest sound ever measured by human instruments. A death toll of over 36,000 people. A pressure wave that circled the planet, recorded passing back and forth as many as 7 times. 4 explosions in under 6 hours. The third one alone reached a point 3,000 miles away. Not for a war, not for a bomb, though the energy involved would eventually get compared to one. This is Krakatoa, a volcanic island in the Sunda Strait between Java and Sumatra. The date is the 27th of August, 1883. The strait today is not empty. Ferries cross it constantly, carrying freight and passengers between Java and Sumatra on one of the busiest short sea routes in Southeast Asia. The Merak Bakauheni crossing alone runs a nearly continuous stream of trucks, buses, and cars. The route passes within sight of the volcano that once erased every town along this coast. Enyer and Karita, the beach towns nearest the old eruption site, now host resorts and dive operators. Boat tours leave daily for a close look at the volcano's replacement. They putter out from harbors built on ground that was scoured clean in 1883. None of this existed the way it exists now, when the island tore itself apart. The coast simply grew back, and people grew back with it, on the same stretch of water that swallowed entire towns in a single morning. 2 completely different kinds of instrument, run by people who had never met, recorded the same event within hours of each other. At the Batavia Gasworks, roughly 100 miles from the volcano, a barometer registered a spike in air pressure. The spike was so severe it strained the mounting of the instrument itself. On the far side of the planet, barographs in London and Washington traced an identical wobble in their ink lines. It arrived on a delay that matched the known speed of sound almost exactly. Neither instrument was built with the other in mind. A gasworks barometer in a Dutch colonial city and a meteorological office in London had no reason to agree on anything. They agreed anyway. The same wave of compressed air had physically reached both of them, a few hours apart, traveling there through nothing but ordinary atmosphere. At the Batavia Gasworks specifically, the pressure spike converts to a sound level of roughly 180 decibels. That figure is measured at a distance of 100 miles from the source. A jet engine at close range produces about 140 decibels. The threshold at which sound stops behaving like sound and starts behaving like a physical blow to the body sits around 194 decibels. Krakatoa's third explosion crossed that threshold at the source and was still measurable as a coherent pressure signal 100 miles away. Ordinary loud sounds fade with distance far faster than Krakatoa's did. Part of the explanation lies in the scale of the blast itself. Part lies in the atmosphere that particular morning. It happened to channel the pressure wave efficiently along layers of differing temperature high above the strait. It worked the way a canyon can carry a shout much further than open ground ever could. The wave did not need to stay loud in any ordinary sense to remain detectable. It only needed to remain a coherent pulse. A sensitive barometer, tuned to catch pressure changes invisible to human ears, could still register that pulse as a single event. There is an older reference to a Krakatoa eruption, and it comes from neither a Dutch report nor a modern seismometer. Javanese chronicles, most notably a text known as the Pustaka Raja, describe a catastrophic eruption on a mountain called Batuara. The event is dated to sometime around the year 416 of the Common Era. The original text gives it as the year 338 of the Saka calendar. It reportedly separated Sumatra from Java and drowned the land between them. Modern geologists remain divided on whether this account describes an ancestral Krakatoa eruption or a later scribe's retelling of a much older flood myth. Volcanologists studying the region independently date an earlier caldera-forming collapse to roughly that same period. Their evidence comes from the layered rock exposed on the islands that ring today's strait. What is not disputed is that the Sunda Strait itself, the water gap between the 2 islands, is largely a caldera boundary. Something enormous carved it open long before Europeans arrived to write anything down. Here is a fact that is simple to check and remains uncomfortable regardless. When Anak Krakatau, the volcano's own successor, collapsed in December of 2018, it sent a tsunami into the coasts of Java and Sumatra. Indonesia's tsunami warning system did not issue an alert. It could not. The system had been built and calibrated to detect tsunamis generated by undersea earthquakes. It relies on a network of seismometers tuned to recognize the specific shaking pattern of a fault rupture. A volcanic flank sliding into the sea produces a different, quieter seismic signature, one the network was never tuned to recognize as a trigger. The technology existed. The specific danger it needed to catch that night did not fit the category the technology had been built to watch for. Ask people to name history's biggest volcanic eruption, and many will reach for Krakatoa's neighbor to the east. Mount Tambora, on the island of Sumbawa, erupted in 1815, rated a 7 on the Volcanic Explosivity Index, one full step above Krakatoa's 6. Tambora killed an estimated 10,000 people directly through pyroclastic flows and ashfall. Tens of thousands more died in the regional famine that followed, as crops failed under the ash. Tambora's ash dimmed the sun so thoroughly that 1816 became known across Europe and North America as the year without a summer. Snow fell across New England as late as June. By raw volume, Tambora was the larger event, and by most measures, the more destructive one regionally. But Krakatoa did something Tambora never did. It happened inside a network of undersea telegraph cables, shipping lanes, and scientific institutions. That network was capable of recording it as a single, coordinated, global phenomenon while it was still happening. Tambora was a bigger eruption that most of the world barely noticed for years. The cables and the scientific societies needed to record it properly did not yet exist. Krakatoa was a smaller eruption that the entire connected world registered within hours. Size alone never decided which disaster became a household name. The surrounding infrastructure did. Why did an eruption in a strait the Dutch had monitored for 2 centuries still kill more than 36,000 people in a single morning? Why does a volcano rated only a 6 on an 8-point scale still hold the record for the loudest sound ever measured? How does a single explosion generate a pressure wave that keeps circling a planet for 5 days without simply fading out? Who decides which coastal warning systems get built for earthquakes and which, if any, get built for a mountain quietly sliding into the sea? How does a scientific mechanism stay disputed for more than a century after the event it is meant to explain? And is the mechanism that broke Krakatoa apart in 1883 still sitting, loaded, in the water that fills its crater today? By the end of this, it will be clear why one Dutch government geologist spent months calling the activity a mere curiosity. The ground beneath him was already counting down. It will be clear why the exact physical mechanism behind Krakatoa's deadliest waves is still disputed by volcanologists more than a century later. And it will be clear why the volcano's successor, born from the same crater, killed again in 2018. It used a mechanism modern instruments still could not catch in time. Every explosive volcano runs on the same basic fuel, pressure. Magma rises from depth carrying dissolved gas, mostly water vapor and carbon dioxide, held in solution by the weight of rock above it. As magma nears the surface, that pressure drops, and the gas comes out of solution all at once. It behaves the way a shaken soda can foams the instant the tab lifts. Scale that reaction up from a single can to a chamber of molten rock several kilometers across, sealed for 2 centuries beneath solid cone. The foam becomes an explosion large enough to be heard on 3 continents. Krakatoa's chamber had been charging under its cones for at least 2 centuries of quiet. The eruption itself was simply that charge finding an exit. The Volcanic Explosivity Index measures the size of that exit on a scale from 0 to 8. Each step up represents roughly a 10-fold increase in material ejected. Mount St. Helens in 1980 was a 5. Krakatoa was a 6. Tambora was a 7. An eruption at Krakatoa's scale happens somewhere on Earth on the order of once every 100 to 200 years. Its last one before 1883 had been at least 2 centuries earlier. The activity did not arrive without warning. Steam and ash first vented from Perbowatin, the northernmost of Krakatoa's 3 cones, on the 20th of May, 1883. Passing ships logged small earthquakes and growing ash columns through June and July. An exploration party that landed on the island that spring found it dusted white, with fine ash, with minor explosions rattling through every few minutes. Some of these earlier tremors were felt as far away as the Australian Northern Territory. That is, thousands of miles to the southeast, months before the climactic morning arrived. None of it looked, at the time, like the opening act of the deadliest eruption in recorded history. It looked like a volcano clearing its throat, something the Sunda Straits shipping captains had seen before and expected to settle down again. The Dutch government geologist R.D.M. Verbeek was already collecting reports from the Sunda Strait through the early summer of 1883. He catalogued smoke columns, ash falls, and the rattled windows of Batavia, 50 miles to the east. Verbeek would go on to write the first systematic scientific monograph on the eruption, published in 1885. He is remembered today as the person who did more than anyone to reconstruct exactly what happened. But in the months before the climax, his own notes used a specific word for the escalating activity. Interesting. Not urgent. Not dangerous. Interesting. The word a careful scientist uses for something he has not yet found a category for. There was no glowing lava lake to point a camera at, no obvious countdown, just smoke, ash, and a pattern of small tremors that did not match anything in the existing catalog of volcanic behavior. This is the uncomfortable center of the Krakatoa story. The instruments were not broken. The observers were not careless. Verbeek was cataloging exactly what a well-trained 19th century geologist was supposed to catalog, and he was doing it correctly. Ships passing through the strait that summer noted the same thing he did. Smoke, ash, occasional tremors, nothing that matched the opening of a catastrophe. What nobody in 1883 possessed was the concept of a magma chamber, quietly losing its roof support from underneath. The surface still looked merely active. The chamber was already changing shape in a way no surface instrument of the era could show directly. The mountain looked the same as it had for weeks. Underneath, it was no longer the same mountain at all. Verbeek would later find a second piece of evidence for just how long this particular charge had been building. Years before the climax, he had examined a fresh, unweathered lava flow on Krakatoa's northern coast. From its condition alone, he judged that it could not have been laid down more than 2 centuries earlier. That estimate lines up almost exactly with a separate, disputed account of an eruption on the island around 1680. That account survives only in a single Dutch etching and a scattering of second-hand reports. Long before any seismograph existed to confirm it, the rock itself was already carrying a rough date stamp for how long Krakatoa had been quiet. Between 5:30 and 10:52 on the morning of the 27th of August, Krakatoa produced 4 major explosions in succession. Each one was larger than the last. The first, at 5:30, collapsed the northern cone. The second, at 6:44, ruptured the middle cone along a fissure. The third, at 10:02, was the one the planet heard. Its energy has since been estimated at roughly 200 megatons of TNT equivalent. That is something like 4 Tsar bombas, the largest thermonuclear device ever tested, going off in sequence within hours of each other. The fourth explosion followed less than an hour later. By then, most of the island no longer existed. The people closest to the volcano left behind some of the only direct testimony of what an explosion at that scale feels like from nearby. The British ship Norham Castle rode at anchor roughly 40 miles from Krakatoa during the third explosion. Half the crew suffered ruptured eardrums from the pressure alone. The ship's log recorded the sound as so violent that the crew believed the last day had come. Several men could not hear ordinary speech again for days afterward. The merchant vessel Charles Ball, under Captain W.J. Watson, came within 10 to 11 miles of the island earlier that same day. Hot pumice rained onto the deck and had to be shoveled clear before it could scorch the timbers. Watson's log describes a sea gone the color of dirty milk, lit by constant lightning. The roaring of the volcano stayed audible for hours before the ship finally cleared the strait. On the Sumatran coast, at Ketimbang, some 25 miles from the volcano, a Dutch colonial official named Willem Beyrink lived with his family. They were caught at the edge of a pyroclastic surge. It had raced across the water from the collapsing island. A pyroclastic surge of this kind carries hot gas and rock fragments at temperatures that can exceed several hundred degrees. It moves fast enough to cross open sea before losing much of its force. His wife Johanna later described the sky turning to total darkness in an instant. A wave of heat and falling ash knocked her to the ground and burned her skin before she even understood she had been burned. The family survived. Roughly 1,000 people in and around Ketimbang did not, killed by heat and ash in what colonial reports afterward called the burning of Ketimbang. Further along the same coast, the Dutch government steamship Beru was picked up by one of the resulting waves. It was carried well over a mile inland, coming to rest measurably above sea level. Its rusting hull remained a landmark there for decades afterward. For months afterward, vast rafts of floating pumice drifted across the Indian Ocean. Some of them carried human remains, swept out to sea by the tsunamis. Reports describe skeletal remains washing ashore on the east coast of Africa as much as a year after the eruption. They had crossed the width of an ocean on rafts of volcanic rock light enough to float. Across both coastlines of the strait, the waves generated that morning reached estimated heights of up to 40 meters. That is well over 100 feet in the worst affected bays. The town of Merak alone was struck by a wave measured at roughly 150 feet, 50 miles from the volcano. The low-lying Thousand Islands were submerged under several feet of seawater, forcing residents to climb into trees to survive. Ash fell as far as 1,600 miles away. The region around the strait was plunged into complete darkness for roughly 2.5 days, as airborne debris blotted out the sun entirely. More than 160 coastal villages and settlements were destroyed outright, with well over 100 more seriously damaged. Dutch colonial records eventually broke the death toll down by region. Over 21,000 died in the coastal district of Banten on Java. More than 12,000 died in Lampung on the Sumatran side, with smaller numbers scattered across Batavia and beyond. The great majority of the eruption's dead drowned in those waves, rather than dying from heat or ash. Almost none of it was captured by any instrument. It survives only because enough people wrote down what they had witnessed before the details faded. It also survives because the Dutch colonial bureaucracy, however imperfect, insisted on totaling the dead afterward rather than letting the number simply disappear. Where the northern two-thirds of the island had stood that morning, there was afterward only open water. The collapse left behind a caldera roughly 6 kilometers across, close to 4 miles. In places it plunged 200 or 300 meters below the surface. Krakatoa had not so much exploded into nothing as sunk into the space its own emptying magma chamber had left behind it. The redistribution of that much mass, combined with the earthquakes that accompanied the collapse, permanently altered the seafloor of the strait itself. It was the kind of change usually measured on a tectonic timescale, compressed here into a single morning. What actually caused the deadliest waves that morning remains, remarkably, an open scientific question. For much of the 20th century, the leading explanation held that seawater poured into the fracturing magma chamber. It supposedly flashed instantly to steam, blowing the island apart from within. In 1981, volcanologists Stephen Self and Michael Rampino examined the actual erupted rock under this assumption. They expected to find the telltale texture that water-driven explosions leave behind. They did not find it. The grain structure of the ash and pumice matched an ordinary, if enormous, magmatic eruption. It was driven by gas escaping molten rock, not a violent encounter with the sea. Their own study effectively ruled out the theory most people still associate with Krakatoa. What actually launched the tsunamis is still argued over by specialists today. It may have been the collapse of the emptying chamber, or pyroclastic flows slamming into the strait at high speed, or some combination of both. The volcano's most basic mechanism remains only partially solved. If a story like this holds your attention, following the channel means catching the next one. There are other islands out there keeping the same kind of secret underneath. News of the disaster reached the outside world with a speed no earlier catastrophe had ever managed. A telegraph station in Batavia relayed word of the eruption within a day. It fed into the same undersea cable network that already linked the Dutch East Indies to Europe for commercial trade. London newspapers carried reports within 48 hours. Illustrated weeklies printed engravings of the eruption within a matter of weeks, based on sketches and photographs carried back by returning ships. No earlier volcanic disaster, however large, had ever been reported to a global audience this fast. Eyewitnesses were still alive to be interviewed, and barometers on other continents were still registering its aftershocks. The eruption's reach did not end with sound or water. Krakatoa injected an estimated 20 cubic kilometers of ash and pumice into the atmosphere. Enough of it was fine, and high enough to circle the entire equatorial belt within about 2 weeks. Global average temperatures dropped by roughly 0.5 degrees Celsius over the following year, with some regional estimates running well above that. It is a small number, but one with an outsized effect on growing seasons across Europe and North America. The same high-altitude haze produced strange, vividly colored sunsets across the world for months afterward, sometimes described as green or copper-colored suns at midday. In Honolulu, an American missionary named Sereno Bishop tracked a faint ringed corona around the sun every clear evening for months. The phenomenon came to be called Bishop's Ring. It is still used today as a marker of major stratospheric eruptions, observed again after Pinatubo erupted in 1991. Art historians have long noted, with appropriate caution, a striking coincidence. The Norwegian painter Edvard Munch described blood-red skies in his diary, written in Oslo in late 1883. The timing lines up closely with Krakatoa's stratospheric haze reaching Scandinavia. Munch's 1893 painting The Scream is sometimes cited as a possible echo of those skies. The connection is circumstantial. It is also difficult to dismiss outright, given how precisely the dates align. Krakatoa's own scientific record eventually filled a single enormous volume. The Royal Society in London convened a special committee in 1884, chaired by the meteorologist George James Symons. Its task was to gather every scrap of testimony the event had produced. Captain's logs, barometer readings, sketches of unusual skies, and eyewitness statements arrived from 6 continents. They came by mail and telegraph over the following months, as the committee's request for testimony circulated through shipping companies and colonial offices worldwide. The final report, published in 1888 under Symons's editorship, ran to nearly 500 pages. It stood for decades as the most thorough scientific study ever produced of a single natural disaster. Verbeek's own Dutch-language monograph, finished in 1885, worked the same event from the opposite direction. It stayed close to the ground rather than across the globe, cataloging ash layers, surviving structures, and the coastline's exact position before and after. Where Symons assembled a planetary picture from scattered fragments, Verbeek rebuilt a local one, meter by meter, from the wreckage itself. Between them, the two reports gave the disaster something almost no earlier eruption had ever received: a complete account. It was assembled from both the immediate wreckage and the planet's own distant instruments, cross-checked against each other, and published for anyone to read. Krakatoa was not the last time this stretch of ocean produced a deadly volcanic wave, and it was not even alone in its own decade. Volcanic tsunamis of this kind remain rare enough globally that each new case still forces scientists to relearn lessons the last one should have taught. In 1888, 5 years after Krakatoa, the flank of Ritter Island collapsed into the sea in a single event. Ritter Island is a volcano in what is now Papua New Guinea. The collapse sent a wave that killed several hundred people along nearby coasts. It remains one of the largest confirmed volcanic sector collapses in recorded history. Like Krakatoa's own collapse, it happened with essentially no contemporary written warning, recorded afterward mainly through the geological deposits it left scattered across the seafloor. The submerged caldera Krakatoa left behind did not stay empty for long, at least on a geological clock. Steam began rising from the drowned crater in December of 1927. By around 1930, a new cone had broken the surface for good and stayed there. Indonesians named it Anak Krakatau, the child of Krakatoa. Bathymetric surveys from as early as 1919, years before anything broke the surface, had already recorded something telling. A bulge sat on the seafloor exactly where the new island would eventually rise. It was a sign that magma was gathering there long before anyone could see it. Once established, Anak Krakatau grew at an average rate of roughly 5 meters a year through its early decades. It built itself up through repeated small eruptions. Eventually, it stood more than 300 meters above the water, well over 1,000 feet. Its base was made of the same loose, unstable material that had failed once before. Closer to home, Krakatoa's own successor produced a small tsunami of its own in 1981, decades before its far larger collapse in 2018. In hindsight, it was a warning sign that the same unstable flank had already started to move. None of these were freak, isolated accidents. They were the same physical process: a steep, unstable, actively growing cone losing its footing into open water. That process keeps recurring on a stretch of the Pacific Rim that keeps building the exact conditions for it to happen again. The 1981 study that finally tested the seawater explosion theory did not begin with a clean answer. Self and Rampino started from the assumption almost everyone else held, that a magma chamber meeting seawater explained the tsunamis. Only the careful grain-by-grain analysis of preserved pumice and ash told them otherwise. Water-driven explosions tend to shatter magma into a very fine, uniform ash, quenched almost instantly by contact with liquid. What Self and Rampino found instead, layer after layer, was coarser, more varied material, consistent with gas-driven fragmentation deep in an ordinary magmatic eruption. It took nearly a century after 1883 for anyone to apply that specific textural method to the deposits Krakatoa had left behind. In the same year Krakatoa exploded, New York City opened the Brooklyn Bridge on the other side of the planet. It was an engineering triumph that dominated American newspapers for weeks. Krakatoa's actual physical mechanism, the detail scientists most wanted answered, would sit unresolved for nearly 100 years. By then, that bridge had already become a historic landmark in its own right. The coastline nearest Krakatoa today is neither abandoned nor unaware. Indonesia's National Volcanology Agency maintains a permanent observation post within sight of the crater, staffed year-round. It watches seismic activity, gas emissions, and satellite radar for signs of ground deformation. The agency runs a 4-tier alert system. Anak Krakatau has spent long stretches sitting at the second or third level. An exclusion zone around the crater expands and contracts as activity rises and falls. Boat operators in Anyer and Karita adjust their routes around whichever level currently applies. None of this infrastructure existed in any form in 1883. All of it assumes the danger will announce itself early enough to matter. Here is the strangest fact in this entire story, and it deserves to be flagged plainly. More than a century of dedicated study, and volcanologists still cannot fully agree on the precise mechanism that generated Krakatoa's most lethal waves. It is worth setting this beside a hazard covered elsewhere on this channel, the Cascadia subduction zone off the Pacific Northwest coast. It is a completely different kind of fault, capable of its own long, silent buildup. Both systems share the same underlying problem. The exact triggering instant, the one moment a modeler most needs to specify, is the hardest part of either system to pin down in advance. Ritter Island's collapse in 1888 gave coastal communities no warning at all, because no warning system for that kind of event existed yet, anywhere. Anak Krakatau's collapse in 2018 gave almost none either, for a more unsettling reason. A warning system existed, but it had been built to listen for an entirely different kind of signal. Indonesia's Center for Volcanology and Geological Hazard Mitigation now runs continuous seismic and satellite monitoring across the entire Sunda Strait volcanic complex. Researchers who later studied the 2018 collapse found something notable. Regional seismic data could, in principle, characterize a landslide of that kind within about 8 minutes of its starting. The tsunami itself took roughly 30 minutes to reach the nearest coastlines. On paper, that leaves a real window, something close to 20 usable minutes, between a fast diagnosis and the wave's arrival. In practice, no alert went out at all that night. The existing warning protocol was never built to trigger on a landslide seismic signature in the first place. The gap was not a matter of speed. It was a matter of the system not knowing what it was looking at. Since 2018, researchers have proposed exactly the kind of rapid seismic analysis that could close that gap. As of the most recent public reporting, it has not yet been built into the operational warning system used along these coasts. Stack the exposure today and the numbers climb quickly. Roughly 1 million people live along the immediate coastlines of the Sunda Strait, in Banten and Lampung provinces. All of them sit within direct reach of a wave generated at Anak Krakatau. The 2018 collapse, small by comparison to 1883, still displaced tens of thousands of people. It injured well over 10,000 more along those same shores. Java and Sumatra together, the two islands the strait separates, hold a combined population well over 150 million. No single nation on Earth held a population that large in 1883. Jakarta, Indonesia's largest city, sits under 100 miles from the volcano's crater. No other coastline on Earth pairs an actively regrowing, historically explosive volcanic island this directly, with so much population on both shores at once. And here is the regulatory gap from earlier in this story, returning with the full picture attached. 8 minutes to characterize a landslide seismically, set against the 30 minutes the wave takes to arrive. That gap describes a warning system that was entirely possible to build well before 2018. It simply was not built in time for a hazard that had already announced itself once in 1883 on this exact stretch of coast. An eruption at Krakatoa's scale, a volcanic explosivity index of 6, occurs somewhere on the planet roughly once every 100 to 200 years. That comes straight from the geological record's own accounting. That is not an abstraction reserved for textbooks. That comfortably fits inside a single human lifetime. A child born on the coast of Banten today has a meaningful chance of living through the next one. It might start at Krakatoa's crater, or at some other volcano keeping the identical kind of schedule. It might arrive within that child's own childhood, or wait for their grandchildren, since the record only gives an average interval, not an appointment. No geologist alive can tell that child which birthday to worry about. One variable genuinely did not exist in 1883, a fully wired, always-on, global network. It can detect an atmospheric pressure pulse the moment it happens, anywhere on the planet. In January of 2022, the eruption of Hunga Tonga in the South Pacific produced a pressure wave that circled the Earth within hours. Modern barometers, satellites, and smartphone apps tracked it, on a scale researchers directly compared to Krakatoa's own. Infrasound instruments built for detecting distant nuclear tests recorded the Hunga Tonga wave circling the planet as many as 8 times. That is slightly more than the historical count attributed to Krakatoa, before it finally faded below the threshold of detection. The tools for noticing a Krakatoa-sized event have improved enormously since 1883. The tools for stopping the wave that follows one have not kept pace at anything close to the same rate. Neither have the tools for outrunning it before it reaches a crowded coastline. Better detection creates a one-directional problem of its own. It raises the expectation of warning without guaranteeing the time to act on it. A population that trusts its instruments can move slower on instinct than one that never had instruments to trust at all. Every generation living along the Sunda Strait assumes the water separating Java from Sumatra has always simply been there, calm, blue, and permanent. It has not. Anyer is an ordinary beach town built on a coastline that a wave over 100 feet tall once erased in minutes. Karita is an ordinary resort strip, sitting within the same exclusion radius that authorities now redraw every time the volcano stirs. Merak, a working port town today, sits on ground where an entire settlement was wiped away in 1883. It was simply rebuilt in the same place, under the same name, by people who mostly never learned what the name used to cost. Jakarta is an ordinary megacity of more than 10 million people. It sits close enough to a historically explosive volcanic complex that its own newspapers carried word of the 1883 disaster within a single day. That news traveled over undersea cable before the story had even finished unfolding. The cable that carried it is long gone. The volcano that generated the news it carried is still there, one boat ride from the same shoreline. If more of these buried patterns interest you, subscribing means you won't have to go looking for the next one yourself. The pattern rarely announces itself with fanfare. It usually looks, right up until the last morning, like an ordinary Tuesday on an ordinary stretch of coast. The pressure wave that left Krakatoa on the morning of the 27th of August, 1883, did not fade like an ordinary bang. It kept going. It kept circling the planet, passing recording stations again and again, logged as many as 7 times over 5 days. Only then did the atmosphere finally stop ringing. This is not really a story about one island in the Sunda Strait. It is a calibration point. It measures what a single mid-sized volcano can do to an entire connected planet in the space of one morning. It also measures how long the resulting silence can last before anyone notices it building again. The mountain that produced it is still there, rebuilding itself, cone by cone, inside the same drowned crater. The mechanism that tore it apart the first time has never been fully agreed upon. The mechanism that made it kill again in 2018 was caught. but only after the wave had already reached the shore. The next reading, whenever it comes, is still an open line on the instrument.